Hello again. This is Math 2232 coming to you from the College of DuPage. The title of this lecture is The Alternating Series Test. As always, please be an attentive learner while watching this video. By way of introduction, the last two tests we looked at for series convergence have required that all the terms in the series be positive. Of course, there are many series out there that have negative terms in them, and so we're going to start looking at tests for those kind of series. But we're going to do something that's very structured. So the test we're going to look at in this section will be a test for what we call alternating series. The definition is, an alternating series is any series, summation a sub n, for which the series terms can be written in one of the two forms. Either a sub n is equal to minus 1 to the nth power b sub n, where b sub n is greater than or equal to 0. Now what this means is that the SIGN of this term is positive and all of the possible negative signage, SINAGE, is sucked into this coefficient. And so this is the ones where the odd terms are negative and the even terms are positive, and this one is the other way about, where the even terms are negative and the odd terms are positive. So that's what this is meaning, and it's like that, and it means it alternates. So if one term is positive, the previous term was negative, and if one term is negative, the previous term is positive, and so on. And it goes both ways. Now there are many ways to deal with this alternating sign, but they all can be written in one of two forms, and either it will be this or this, but it could be written various ways. For example, if we have minus 1 to the n plus 2, well, minus 1 squared is 1, so that's really like minus 1 to the n. And down here you will get, if you write it as n minus 1, that's the same thing as breaking it up this way. This one will be positive, so you can write these many different ways. But there's the basic pattern that we spoke of up here. And so if you run into one of those different forms, just convert it to this and you will be fine. Here is the statement of the alternating series test, and we'll give a proof later, but we're going to use it first. But let's begin by having a clear statement. Suppose we have a series, it is summation of a sub n, and it is alternating series. That means either a sub n is of this form or a sub n is of this form. So first of all, to apply this, it must be an alternating series. And again, I'm stressing that there is no SINAGE signage associated with B sub n. B sub n is always positive. Now here's the if part, and there are two conditions that you need. If the limit as b of b sub n as n tends to infinity is 0, that's the first condition, and the second one is bn must be a decreasing sequence, then this sequence will converge. So there's a couple of things to note about this test. First, unlike the integral test and the comparison/limit comparison tests, this test will only tell us when a series converges and not if it will diverge or when it will diverge. Secondly, in the second condition, all we really need to do is say eventually the BCNs will be decreasing, because the first finite number of terms doesn't really matter. It's all about the tail. So all that's really required is for the b sub n to be bigger than or equal to b sub n plus 1 after some point. And this kind of explains that, but I've talked about that. And finally, note that in practice we really don't have to strip out the terms. We just have to note that eventually the series terms are decreasing. Then we can apply the test and determine convergence. Examples, and I won't break these out separately, but always these are good examples to do while you're reading. Try them first, and also for reviewing. Try them because these will be the statements. So example 1, determine if the following series is convergent or divergent. Is a summation from n equal 1 to infinity minus 1, whole raised to the n plus 1 divided by n. And you should write out a few terms here to see what it is. So what we're going to do then is when n is equal to 1, it will be 1/2 minus a third plus a fourth, and so on. So let's solve this problem. So first we identify b sub n, and b sub n is 1 over n. Again, the sign is separately structured. So this is the same thing as this, and that is b sub n. So it is an alternating series, so now all we need to do is run through the two conditions. Well, the limit as n goes to infinity of 1 over n is indeed 0. And if we make the denominator bigger, the fraction is smaller. And so this is a decreasing sequence. So both conditions are met, and so by the alternating series test theorem, the series converges. Now this is a well-known series. It does have a name. Since this was the harmonic series, we will call this the alternating harmonic series. And it was easy to see that these terms were decreasing here, so that was easy to show. In more complicated versions, this says you want to use calculus, and that means take the derivative. And if the derivative is negative, that means that the sequence is decreasing. And so that's an important part of our pedagogy. Another problem. Again, this is a good problem to practice now and later. Determine if the following series is convergent or divergent. So this is the summation n equal 1 to infinity of minus 1 whole to the n. That's n squared over n squared plus 5. So first, we're going to identify, first we verify it is alternating, and it is, because n squared and n squared plus 5 are both positive. That's our b sub n, and this is an alternating thing. So let's check the conditions. Well, as n goes to infinity, what happens with the b sub n is it's equal to 1, and that's not equal to 0. Well, right away, we don't have the first condition met, so there's no reason to check the second. Now, that tells us that we're not going to be able to use the alternating series test to conclude this converges, but we could use another test or think about the problem more deeply. So we'll think about the problem more deeply. And the more deeply thinking about this goes back all the way to our very first consideration, which was called the divergence test. And remember that if a sub n doesn't converge to 0, or the individual things don't converge to 0, then the series diverges. So the divergence test requires us to compute this, the limit as n goes to infinity of minus 1 to the n all over this stuff. Now, this could be tricky, but if we write it this way, it's pretty clear to us that this is going to converge to 1, and this is not going to exist. It's going to bounce back and forth between minus 1 and 1. So it's pretty easy to conclude that when we split it up this way, that this limit doesn't exist, and if the limit doesn't exist, then that means by the divergence test, this series diverges. Example 3. Here we're to determine if the following sequence is convergent or divergent. So this is going to be the sum from n equals 0 to infinity. This is minus 1 to the n minus 3. Square root of n over n plus 4. Again, a good problem to practice. Notice that in this case, the exponent on the minus 1 isn't n or n plus 1. It's n minus 3, but we do realize that as n grows, what will happen is that this will alternate, so that's fine. So let's check the conditions. And moreover, the bn's, if you strip out the alternating component, that this is positive. And so now we need to know, does this go to, in fact, so we need to know, is this decreasing? And we also need to know, is the limit equal to 0? Well, when you do this, you can divide top and bottom by square root of n, and you can conclude that the limit of this is 0. So that is good. So now all we have to do is verify that it is decreasing. Well, as we warned before, the best way to do this is to think about the calculus and compute the derivative. So if f of x is equal to the square root of x over x plus 4, taking the derivative is going to involve the quotient rule. And so you have to remember that. So it's the denominator times derivative of the numerator minus numerator times derivative of the denominator, all by the denominator whole squared. And if you simplify that, you get this. Now, if you look at this, you can say, well, this the denominator is always going to be positive, and this is going to be negative after 4. But the first few terms aren't there, but we don't care about the first few terms. It's all about the tail. So it matters what happens at the end. So we can conclude that after 4, that this is decreasing. Okay, and there were 2 critical points, and that x equal minus 4 is not a critical point because it's not defined there. That the derivative is not defined there, but what we can see is that this is decreasing on n greater than 4. I think I already talked about that. So these are eventually decreasing, and so the second condition is met. So both conditions are met, so by the alternating series test, the series must be converging. Now, this example shows us that we sometimes need to do a fair amount of work to show the sequence the terms are decreasing. Don't just assume that they will be decreasing, because that is a condition of the theorem. Another example, determine if the following series is convergent or divergent. So this is a summation from 2 to infinity of cosine pi times n, cosine n pi, divided by the square root of n. Well, you might say, why is this in a chapter on alternating series? But you see, if you study the cosine of n pi, you'll find that the cosine of n pi is minus 1 to the n. It depends on what n is. The cosine of 0 is 1. The cosine of pi is minus 1. The cosine of 2 pi is 1, and so on. So we check some values, and we can see that that's true. So this really is an alternating series, and the b sub n, in this case, if I strip off the sign, I get 1 over the square root of n. Well, as n goes to infinity, this does go to 0, and so that is one of the conditions that we need. And as we make the denominator bigger, they're smaller. And so both conditions are met, so by the alternating series test, the series is convergent. Let's talk about the proof. Without loss of generality, we can assume that the series starts at n equal 1. And if not, we could modify it, so that's what without loss of generality means. And also, we have an equal minus 1 n plus 1 over bn, because we know that this is an alternating series. Okay, so all we really needed to prove was for the bn to be positive and eventually decreasing. For the proof, what we're going to do is we're going to say they're positive and that they're decreasing for all n. And again, this is without loss of generality. And then we're going to look at the difference between bn minus bn plus 1. And again, we're assuming that these are positive and decreasing. So this difference then is going to form a sequence which is S sub n, and let's look at the partial sums. So S2 is just going to be B2 minus B1. S4 is going to be B1 minus B2, B3 minus B4, and so you see what we're going to prove is that the sequence, and this is a subsequence, S2n is an increasing sequence. So here we're just taking the terms that result in a positive difference between these. So this is we're adding this difference in, and so we've formed a increasing sequence. And the general term can be written this way. We're just doing some clever writing of the parentheses. Now each of these quantities are positive, and so we know that this subsequence is also positive, and so that tells us that S2n for all n is less than b1. That tells us that this sequence is bounded. So we know it's an increasing and bounded sequence, bounded above, so that means there is a limit, but this limit has to be the same as the limit of the odds, and we can observe that in the following way. So if we let n go to infinity of S2n plus 1, that is going to be S2n plus B2n plus 1. So this one is going to give us S, and this is going to go to 0 by our assumption. So we know both S2n and S2n plus 1, the evens and odds, are convergent sequences. So they both have the same limit. And so we know that this is a convergent sequence with limit of S. And that tells us that the summation A sub n is convergent. You want to spend some time thinking about this proof. But now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.